Let's take a look at an example problem from Module 14. So in this problem here, they tell us that we have an elevator car, E, and this car has a mass, ME, given to us as 1.8 megagrams. So this is our elevator car right there. They also tell us we have a counterweight C, so here's our counterweight C right here. And this has a mass, MC, is equal to 2.3 megagrams. Now, if a motor is going to turn this driving sheave A up top here with a constant torque, the M, given to us here as 100 Newton meters, shows our M right there, and there's our motor right there, they're asking us to determine the speed of the elevator, so the speed of E right here, when it's ascended a distance given to us as S is equal to 10 meters, starting from rest. So we know if it starts from rest, that means our initial velocity is 0. So that's some useful information as we're solving through for this problem. They also tell us now that each of these sheaves A and B, so up at the top here A, down at the bottom here B, they're going to have an equal mass of MS equal to 150 kilograms. So again, pay attention to our units here. These are in kilograms, or as we noticed before, our other masses are in megagrams. So make sure we do the correct unit analysis when we do this. They also tell us that we have a radius of gyration given to us as K is equal to 0.2 meters, about its center of mass at the pin axis right there and right there. And as far as assumptions, what they're telling us is that they want us to neglect the mass of the cable, so we're going to assume a massless cable, and also assume that the cable does not slip at all. The last thing that we can see here is we can see the radius of each of these, they're equal, and that's R is equal to 0.35 meters. So they give us a lot of information between the problem statement and the initial diagram that we're going to want a way to organize neatly and be able to reference back to as we're solving through for the speed of the elevator. So now that we've had that opportunity to read through the problem statement, take a look at our initial given diagram and all the wording, what we want to do now is create our setup page. And on the setup page, we want to organize all that information that's given to us in the problem statement into a nice, clean way to reference back to. So the first thing we want to do is take a look at everything they give us in the problem in the diagram, write it down neatly here with the correct units and variable names. So we see here we have our M sub E given to us as 1.8 megagrams, our M sub C as 2.3 megagrams, our moment M as 100 Newton meters, our mass of A is 150 kilograms, our mass of B as 150 kilograms. Again, pay attention to our units, megagrams or kilograms, and make sure when we plug in we're using the right units and do the conversion correctly. Our radius of gyration is 0.2 meters, our distance equal to 10, S is equal to 10 meters, and our radius here of 0.35 meters there. Again, they asked us to solve for and find the velocity of our elevator, V sub E, right here. And the assumptions we're making is that there's no slipping and it's a massless cable. And we redraw a simplified version of our diagram there. A and B right there. There's our counterweight C and our elevator E right there. And we can see there's our moment and our radiuses. So now that we have all the information in one spot that's easy to go back to, understand what they've given us and what they're asking us to solve for, then what we can do is to begin our solution. To begin our solution here, we want our governing equation. So our governing equation here is we can find theta based off the relationship of S over R. So this is equal, we know this information, we know our S is given to us as 10 meters in the problem statement, and our radius is 0.35 meters, so we can plug directly in here in order to get our theta term here. So we find that our theta is equal to 10 over 0.35. Now from there, the next thing that we want to do is take a look at our principle of work and energy. So with this here, we recall our general equation for principle of work and energy. T1 kinetic energy plus the summation of work here from 1 to 2 is equal to T2 kinetic energy 2. Where, in this case here, our initial kinetic energy, because it's not moving, it tells us it starts from rest, this is going to be 0. So this is going to simplify this part down of our governing equation there. So for the next part of our solution, what we want to do is create our free body diagram. Now the best way to create our free body diagram is reference back to our given diagram here, simplify it down, and figure out everywhere that we have a force acting on it. So what we can see is we're going to have at point A and point B, we've got these pins here. So what we're going to have at A and B are reactionary forces. We're going to have reactionary forces in two directions, our X and our Y direction. So we want to establish what's going to be X and what's going to be Y. We could go with a standard Cartesian coordinate system. We call X positive to the right and Y positive up, or we can modify it from there. But regardless of which we choose, we want to pay attention to our sign convention and be consistent with that throughout the problem. So for the free body diagram, we reference back to that initial given diagram there, and we say, okay, here's our A sub x and our A sub y for our reactionary point forces at point A here at the pin, and here's our B sub x and our B sub y, our reactionary forces at our pin down here at B. Now we can also say, well, we're also going to know that we have a mass for A and a mass for B here, so that we can have a weight force. Our weight force is going to be our mass in kilograms times our acceleration due to gravity. So in this case here at point A, we have our mass of 150 kilograms times 9.81 meters per second squared. So that gives us newtons there for our weight force at point A. We've got a weight force at point B here, which is our mass of 150 kilograms times acceleration due to gravity of 9.81 meters per second in units of newtons, and this is our weight force now given to us here for point B. Now we're going to have two other weight forces here. We're going to have the weight force here from our counterweight C, which is our mass times acceleration due to gravity at C, and we're going to have our weight force over here from our mass times acceleration due to gravity of the car at our car E. So all of that goes together to create our free body diagram that we can use and create from our initial given diagram over here on the left and all of the information given in the problem statement over here on the right, which I just copy and move over here just so I can reference this as I start plugging in for all of these weight forces there. So for the next part of our solution, we're going to take a look at work. So if we recall back to our principle of work and energy we looked at earlier in our solution here, we had the fact that we had kinetic energy 1 plus the summation of our work from 1 to 2 is equal to T2, kinetic energy 2, so where initially it starts from rest, so our T1 was equal to 0, so this goes to 0 there. So now what we're going to focus on is this portion right here, our work from 1 to 2. So work's going to be a force times a distance here. So we can see is we have our force here is going to be our weight force for our car E and our weight force here of our counterweight. And we're also going to have the work from our moment times our theta term there. So now we know we have values here. We got weight is going to be our mass times acceleration due to gravity. Our distance here is that S is equal to 10. That's the distance it's going to move here. So that's 10 there. Same thing for our counterweight here. Our work of the counterweight is the mass times acceleration due to gravity times our distance, our Y sub C here, which is going to still be that same. It's all connected by that cable that's moving that same distance of 10. So we can plug that in there. Plus they're given our moment here is 100 and Newton meters, and our theta we just solved for above here by this relationship here. Theta is equal to our S over R, so that angle there is equal to the 10 divided by our 0.35. So this ends up being, when we do out our math here, 28.57 for the angle there. And we do out our math for this whole thing, we find that our work from 1 to 2, when we plug everything in, is 51,907. So for the next part of our solution, we're going to take a look at energy. So again, if we go back to our governing equation here, recall we had the principle of work and energy. T1 plus the summation of our work from 1 to 2 is equal to T2, where we saw again our T1 was 0 because it starts from rest, so that goes away. Now we've already gone through and solved for our work from 1 to 2. So the last thing that we need to solve for here is our T2, our kinetic energy here. So kinetic energy term we have given right here, our T1 is equal to 1/2 me v squared, mass times 1/2 mass times velocity for our elevator there. There's our velocity right there, plus our 1/2 mc, the mass of our counterweight times the velocity v squared right there. Now, plus our last term is our radius of gyration. We have two masses ma and mb are the same, so we have 2 times 1/2 ma, which those masses are both the same, times our radius of gyration here, squared times our v squared over r. So now what we can go through is take a look at everything that we know we have and given us in our problem statement, which I've put up above here. So we have our mass of E, mass of C, our moment, mass A, mass B, and our radius of gyration here. So we can start plugging those guys in. So our ME we plug in is 1800 or 1.8 megagrams. We convert to kilograms here, times our v squared there, plus 1/2 of our 2300, which is our m sub c here, or 2.3 megagrams when we convert to kilograms, plus 2 times 1/2 of our mass here of A and B, which is 150 kilograms, which we can see is given to us there, times our radius of gyration here, which is 0.2, all over a radius, which is 0.35 meters. So we can simplify this down and reduce it, and what we end up with is T2 is equal to 2099 V squared here. So for the last step in our solution here, we go back to that key governing equation, our principle of work and energy. So again, we have T1 kinetic energy at 1 plus the summation of our work from 1 to 2 is equal to kinetic energy 2, or T2 there, where now we've already again determined, starts from rest, T1 is 0, this goes to 0. So now on the left-hand side of the equation, we have the summation of our work from 1 to 2 is equal to T2 on the right side of our equation. Now we've already gone through and calculated the work, or U1 to 2 right here, and we have a numeric value of 51,907. So this value right here can plug in right there, and this is now equal to T2, where we just solved that our T2 is equal to 2,099 V squared. So we can plug that in right here for our T2 value, take this right here, plug it right in there, and what we end up with from our new version of our principle of energy, once we plug in our known values there, that our work from 1 to 2 is 51,907 is equal to our 2,099 V squared over here. So our only unknown in this is our V squared, which is exactly what we're looking for, the velocity of that car E. So we do our math here, and we find that V is equal to 4.97 meters per second squared. And again, the whole way, please keep track of your units and do your right conversions in order to get the units right at the end here. And this is a double check. This should be in meters per second.